try with a little help of my friends here. So we got the power of three here with Patrick, Mark, and myself. So hopefully, I'm thinking we're pretty confident that you can try to stump us with questions, but we'll see what we can figure out here. Let's get going. It does take, like I say, we were around an hour or so yesterday on this little presentation. So it's an overview of the Vitocal 100 air to water heat pump, AW. AM2V is what we're going to be going through here today. So if you're looking for something different, then maybe we signed up for the wrong webinar here today. But it's all going to be heat pumps today. I'm going to try to keep boiler off of my mind, although there are some boilers pictured in here. But see how long it takes before I call this a boiler as we go through. It wasn't very long yesterday before I called it one. So sit back, finish up your coffees. I know everybody's still in the morning here that's online with us right now. So enjoy your caffeine while Patrick and Mark and myself will take you through identifying the key features of the benefits of the Vitocal 100 air to water AM2V. We're going to describe the built-in benefits of the indoor unit. So it comes as a package. You're going to see that shows up on site there, and there's going to be some components that are going to be outside and inside that we'll be describing and showing you here shortly. And identifying the installation advantages. So we're going to look at a couple of common applications, both standalone and with backup boilers. I tripped up a little bit yesterday, and there are some really good application drawings that Mark and Patrick have done. And I forgot to kind of describe why we pipe the backup boiler the way we do, and not directly to the buffer tank, as you'll see here in a little bit. It'll all make sense as we move through here. I just want to kind of mention that at the beginning, just to remind myself to point that out, why those piping arrangements look like they do on the schematics. So the first thing we're going to talk about is why we named it the way we named it, the nomenclature of the heat pump itself. It's a Viessmann product here in North America. So like our Vito Dens and Vito Crosal boilers, and you go back a little bit, more in time, it's the Vito Ron, that sort of thing. Vitocal is the segment name that we've gone with. So that's our heat pump segment. It's a 100 series, and you do see that there are other 200s and 300 series. Those are kind of things that are in the planned in the future, and and you'll see some very interesting kind of innovations as those products come out. Air to water is our product. So you see the different types of heat pumps that we'd be looking at in that segment. So AW, air to water. The generation is an A generation. This is the first generation we're going to bring to North America, although we've been making heat pumps in Europe for a number of years. And it's a monoblock configuration. That means that the refrigerant portion of the heat pump is all in one single package. It's all enclosed in that outdoor unit. It will come with two pieces, the outdoor and the indoor unit. We're going to describe the indoor unit and its function with the outdoor unit here in the coming slides. So that's the two that we have there in the product nomenclature. Variable speed, so it's a modulating heat pump. The compressor is going to match the load of the building to a point, and so it's the V there for variable speed. So just like a boiler, there's a turn down that we've got to think about. And we will show you or give you the information in BTUs as far as the highest cooling capacity first. So this is the smallest of the three units, the 020. 020 is the cooling capacity, 20,000, and 28,000 as far as the heat capacity for that 028, 028 heat pump. And we've got three different sizes. This is the smallest of the three that we're depicting here for your information. So that's the nomenclature. The actual products you'll get, as far as their testing and certification, there is ongoing certification that's happening right now for things like Energy Guide and those sort of things for air to water heat pumps. The industry's kind of catching up to the manufacturing of these products. So you will be seeing some of those things coming in the near future, as well as your different type of Energy Guide ratings and those sort of things. But we have an AHRI certified Intertech ETL certified outdoor unit. You'll see that in the bottom left-hand corner. There's going to be 3 sizes to those we're going to look at. The UL certified indoor unit. I actually was at the Waterloo facility and saw all, a lot of the molds and the things they had to make for testing of these boilers for things like skin temperatures and stuff for safety. So it was pretty interesting to have a look at what was going on there in the at our test facility in Waterloo. So the indoor unit, we have a buffer tank. You'll see there kind of center right at the bottom. That will come with the other 2 pieces that I mentioned here already. So all those 3 pieces here will come on a skid. That will so that it comes as a package, 1 SKU for the wholesaler to deal with. And then optionally, we're going to have domestic hot water tanks specifically manufactured and available for the heat pumps. It's just the surface area of the heat exchanger we're talking about there. We'll have a discussion on those tanks as we move forward here. They are Intertech certified as well as far as the listings go. So these 3 pieces here are essentially 1 SKU, 1 product on a skid that you're going to get. And then the option of adding domestic hot water functionality is available as well for these outdoor unit or these heat pumps. Conceptual schematic or kind of arrangement of what they would look like kind of sitting in your facility or your home. But you see that you've got the outdoor unit, and the connection between the outdoor unit and the indoor unit will be there'll be a communication cable between those 2, so they'll be talking together. And as well, you're going to have the piping, which is typically going to be a 1-inch PEX connection from the outdoor unit to the indoor unit. From the indoor unit, which is sitting on the wall right here, we're going to go to that buffer tank, which is sitting on top of the indirect tank in this picture. And from the buffer tank, it goes to the air handler here. So we're providing heating and cooling through like a chilled water type of capacity on the cooling side. And obviously just traditional hydronic heating for the air handler when we're in the heating season. And also the indoor unit here is going to be piped and connected to the domestic hot water tank via the ability of doing priority here as far as domestic hot water over space heating. It'll have that functionality as you'll see as we move forward here. The other option there to look at, very similar drawing with this one here. However, we have a backup heat source. So we have a gas-fired modulating condensing boiler sitting next to the heat pump indoor unit here. And if you're in a region where your design temperatures start dipping down below the capacity of the heat pumps, you'll have backup heat sources, whether electric or gas or some other fuel source. And there is the ability of enabling and disabling those backup sources through the indoor unit, so it can act as a package. Here, a little bit of picture of the buffer tank sitting on top. You can see kind of it turned around. You can see one of the tappings on the face of that buffer tank. We'll describe all those here momentarily, but that's kind of a concept of what you can kind of expect to see when you're dealing with these types of components and how they're going to lay out there in a building. The packages, so kind of going through a little bit more detail about those packages that have the certifications we just reviewed. We are dealing with, like I say, the outdoor unit is what you see here. This is the monoblock component. All of the refrigerant components are built into this unit here. It sits outside. It is an R32 refrigerant. R32 is fairly new to North America. It's been used in other countries for 10, 12 years, so it's not really a new as far as the worldwide usage of this particular refrigerant, and it has been used as percentages of other refrigerants that you guys have been using commonly here in North America. So it might be blended with other refrigerants, other components to make a refrigerant that we use here locally. But we will discuss the R32. It's an A2L refrigerant. We'll talk about that flammability and all that stuff moving forward. The compressor is variable speed, as I mentioned, so it's modulating compressor, as well as the fans will essentially RPM will change based on the load of the compressor as well. And you see the 3 units here, the largest one having 2 fans, and the smaller and the medium size unit having a single fan capacity there, but those are variable speed. we'll detail a little bit in a parts breakdown of what that fan. There's a shroud and stuff built around it. We'll talk about that for wind a little bit later on. There is a crankcase heater on the compressor that will basically there for colder weather climates and stuff to keep the compressor warm in those areas. It also helps to on the base pan side of the system as well to keep all the stuff warm in those colder climates. Little strip heater. And the outdoor units that you see here will always be matched to a specific indoor unit. So there's 3 outdoor units. There's going to be 3 specific indoor units for those, and those be matched in everything from flow rates, capacities, backup as far as electric, all that stuff will be matched to the outdoor units. The buffer tank, we'll look a bit deeper in here as well, how that all pipes together. And the schematic that we looked at there, the couple of pictures we showed of the system piped up, you saw one what we call a heat cool circuit, as we were talking about earlier in the before we started the presentation. There's the option of adding a mixing valve to your indoor unit to operate with a sensor, et cetera. And now you can have 2 different temperatures as far as heating goes. So we could have a heating circuit too on a mixing valve, throttling that temperature based on your heating curves, outdoor reset. In the cooling season, that mixing valve is just stuck in the wide open position, but you can still do radiant cooling through that circuit as well in the should the time of year require you to cool the building versus heat it. And then we'll also have a look at those optional tanks that are not part of the package, that they're optional, that you can purchase, and they're sized specifically for these heat pumps to scrub as much heat off of that heat pump as possible and dump it in your indirect tank. We'll look at that a little bit later on. This is just off the technical data manuals for these. These are now available online. So if you go to our websites, whether you're in the US or in Canada, you go to our websites there will be a product information on our website, and there will be heat pumps in there, and all of the documents are living in that spot for now. And like I say, they'll be updating those as time goes, but we have the manuals available there for you to have a look at after the presentation. You'll notice that we don't give you a specific BTU or cooling load capacity here. We say refer to charts. We're going to look at those here momentarily just to give you an idea that everything's based on the ambient temperature that outdoor unit's sitting in. What capacity it's going to give you, what temperature we're going to be able to give you will be essentially based on what we see outside. So we'll have a look at that here in a bit, and the importance of design, temperatures and operation. Looking at what we're trying to send out for heating and cooling to make these things kind of, put them in the right spot as far as your buildings and your requirements. The A2L refrigerant R32. As far as the electrics on this thing, your energy, your power requirements, it's a 208-230 single phase heat pump. All 3 of them come in that configuration, but you do see the total amp draw, your circuit breaker sizing will change as you go from the smaller unit here, which goes from about a 17 minimum circuit to a max of 25. We got a 28 to 45 in the 034043 as far as your breaker size, and 44 to a 70 as far as the max on that goes. So you can get your idea of what your requirements are going to be based on those minimum and maximums that we're dealing with. Your air temperature range for the guys out there that are heating designers, you can see that it does capture quite a bit of the the heat design temperatures that we use here in North America, down to minus 25 C up to plus 43 degrees Celsius, so minus 13 Fahrenheit to 109 Fahrenheit, so depending on heating or cooling. So it does have a fairly large range of capability and operation with some of the built-in stuff we're going to talk about. Enhanced vapor injection and the R32 refrigerant helps to get us to those capacities. The water flow range on the indoor units, it has a built-in circulator, and you can see the smaller units, that pump is ECM, so we can adjust the flow rates, but we go from about 3.7 to 8.8, 6.2 to 15, on the middle unit there, as far as your flow rate ranges, 11.4 to 25.5. Pressure drops through the heat exchanger on the glycol refrigerant heat exchanger there are rated in the manuals as well to give you some idea of what residual capability is left over in those pumps. And that's going to determine essentially how many feet of 1-inch PEX you can pipe between the outdoor unit and the indoor unit. And there are some limitations there that we can talk about a little bit later on. The minimum flow rate, there's a flow switch built in, and we're going to talk about and discuss safeties in the outdoor unit a little bit later on. But for now, suffice to say that each unit has the same flow switch in it at 1.75. So if we don't make 1.75, that flow switch doesn't close. It's going to essentially block the compressor from starting. So we don't have, we need a load on that compressor before we fire it up. And here are those graphs we were talking about. So as a heating designer, what you're doing is you're looking at these graphs and you're looking at your supply wire temperatures that you're going to get and outside temperatures here. So you can figure out where your design temperature sits here, what your required supply wire temperature is going to be. And we can get an idea of the performance of these heat pumps in those particular environments and whether or not you might need to have some backup energy sources to supplement the heating of the space when you get down to lower temperatures and what the capacity of these heat pumps can give you. But just an example, one design is in the top there at 95 Fahrenheit with the red circle, 35 degrees C supply temperature going out. And then we selected something that's about 55 degrees, about 20 degrees C higher temperature in the blue line here with the black circle. And you can see at 7 degrees C outdoor temperature, about 45 degrees Fahrenheit, you have a COP of just over 2 on the if you're supplying 131 degree Fahrenheit supply temperature versus a little over 4, so about twice the COP or performance at that 20 degrees C lower supply temperature when it's 45 degrees outside. Now that same temperature as we get colder, so we get down here and we're at about minus 10 degrees C. So if we got anybody that's up early this morning that's from the lower mainland area in Vancouver, this is kind of our design temperature here for space heating. So we're looking at about 10 degrees, minus 10 degrees C or about 14 Fahrenheit. And you can see that if we had this, the smaller heat pump, this is the 020028 heat pump, that we would be at 95 degree Fahrenheit, we would have a COP of just, about 2.35, 2.4, versus if we are trying to send out 131 Fahrenheit, we're just above 1 here as far as the capability of the heat pump. So the design is obviously going to be important here. It might require retrofit applications, maybe looking at supplemental, maybe adding more baseboard to a system, or maybe you're looking at, an air coil or air handler or something like that. Maybe you go to a larger sized air handler that we can actually lower the supply temperature down a little bit to get it into those sweeter spots as far as the heat pump performance goes. But even if you look at this graph, the 95 degree Fahrenheit supply temperature here, at the design here, the COP is actually still higher than us designing at 131 Fahrenheit at plus 7 degrees. So it gives you an idea there, the importance of us if we want to get as much efficiency. It's like installing a condensing boiler and operating at 100 and at a high temperature. If you want to get the benefits of the unit, we want to make sure we design it for the appropriate temperatures that the thing can perform well in. So that's your 020028. If we look at it on the other side of the thing, not COP, but actual designing for your heating capacity that you're requiring in BTUs. So this is the 28,000 BTU unit. And we can see, based on our design temperatures here, the different graphs that we have, different curves that we're looking at here. If we're designing for at 140 degree Fahrenheit to temperature, we are going to be limited to somewhere about 5.5, 6 degrees, about just around 5.5 degrees Fahrenheit or so, outdoor temperature ambient, and the heat pump won't be able to achieve that 140. So we're looking at that temperature dropping down here. So if I'm a designer, I'm looking at, if I have a temperature that I'm dealing with here, I can look at where that's going to start to cut out and where my backup heat source is going to be kicking in as far as temperature. So I can see at, 140, I'm over here at 27,000 BTUs or 28,000 BTU, sorry. If I was going for 95-degree water, I'm way over here now at about minus 13 or so as far as the design temperature degrees Celsius. So it makes a big difference, what our actual carrying capacity of this heat pump is going to be, and what the design temperature is, and when it's going to drop down below the line, and when that backup source is going to have to kick in and supplement our space heating. So that's the heating side of it. If we go and flip over to, where we're getting into here now on the, getting spring and soon summer will be here, and we'll be flipping the switch from heating to cooling. You get the idea here is our cooling coefficient performance here. On the graph, we see some of the load information in the little supplement at the top here from the technical data manual. And you see from, if we were getting 45-degree Fahrenheit leaving supply temperature for cooling out to the building, 7 degrees C. At 95-degree Fahrenheit outdoor temperature, we're at 100% load here. If it's at 80-degree Fahrenheit, it's at 75%, 65, and 25 at 55 degrees outside. So you can see our load percentages here are changing. When we look at this number down at the bottom, this 4.867, our integrated part load value, it's just a weighted average of these. So, how much time this heat pump will spend in this particular part of the load, et cetera. And this kind of value is supplemented in a lot of heat pump almost said boiler, heat pump manufacturers literature now to give you kind of a more of an idea of its seasonal operational capabilities. So the weighted average of where it's going to be as far as percentages and loads, and what you can expect that performance to be. So it's kind of another average there of the performance of the heat pumps in the cooling area to give you some information about comparison of apples to apples in these systems. So if you have a modulating heat pump, they can use as an integrated part load value calculation. But we see here that we've got 81-degree Fahrenheit, 27-degree outdoor temperature, and 43 degrees. So the kind of extreme portions on the season there. Will still be some area here that we'll be talking about cooling as well. But we drop about a ton or so as far as performance from that temperature, change 16 degrees Celsius here from 27 to 43. So these graphs are all in the documentation, the manuals, and each of the 3 units will have its own individual graphs that you can see here. So you're always comparing, effectively what the capacity of the unit's going to be in heating or cooling, and what its power consumption is going to be. So when we get to essentially the same amount of capacity and cooling as power consumption, we're kind of sitting at this spot right here, the little intersection where we intersect the 2 lines. And the idea is that we're operating the heat pump where we're getting more capacity out of it than what we're spending as far as the kilowatts information. So our EER here number, the higher this is, the better that performance of that heat pump is going to be in the cooling phase here. So all these graphics are going to be in the manuals. Again, this is all depicting the smaller unit, the smallest of the 3 units that we're showing off here. But just that criticalness of where we're going to be sitting in your outdoor area. Mine's going to be very different here as far as design temperatures than, say, Patrick, who's in New York State. Mark being in Ontario, just a little bit north of Patrick, they might be a little bit closer as far as what the humidity, that sort of thing is going to be like in the cooling season. Us on the coast here, it'll be a little bit different, and of course, where we're going to design will be a bit different here as well. The final little bit about the outdoor unit. So that was all about performance and stuff of this outdoor unit and the graphs that you're going to see there. But you can see the rest of it here. So the heating capacity of the units themselves from 20,500 to 58,000 BTUs, depending on the size of it. So we're going to kind of select a unit based on our requirements and where this is going to fit. And then our range for cooling capacity for the 3 units is in there. And then the appropriate EER and COPs for the different units are also depicted in this little schematic arrangement here for us to look at, which kind of leads us to the performance of the outdoor unit when we basically match it to the indoor unit as far as the performance of that system is going to be. There's a few things that you got to consider and think about when we're taking that, moving that heat from the outside to the inside, or moving the heat from the inside to the outside, but we're in heating or cooling. And we've done some of that math for you already. We've matched a appropriate unit in there as far as the pump size and capacities to look after what the outdoor unit can deliver to us. The ability for us to split the loads. So now in the heating season, we can actually have two different temperatures. So that allows us to really open up design there significantly, where we can add more capacity, say if in a retrofit application, or we want to do some different temperatures of sensible and latent cooling. It really opens up a lot of ability for you as an installer for that homeowner's request, and kind of match those expectations. The automatic, it's not an automatic switch over between heating and cooling. It's a manual changeover. There's a dial on the outdoor unit here, we'll see. And we're going to toggle that from the heating season to the cooling season and make those switches. Inside of the unit, it has there's a lot of sensor connections in there for different loads and applications that you can do. We're going to have a sensor that we can install into the buffer tank, which will essentially allow us, the indoor unit, to monitor the temperature in that massive fluid in there, and make sure we get the appropriate cooling, chilled water temperature, or supply heating temperature for that heating chilled water circuit. The control will also look after your domestic hot water loads as well. Excuse me. There is a sensor that comes with the outdoor unit. Excuse me for a second. Mark will have to work his magic on that one there and edit that one out. But we've got a control on this indoor unit that can manage your DHW operation and give you some priority levels and adjustable temperatures and day timers and that sort of thing for your DHW loads. And we've got a separate outlet, which allows us to do priority. So there's a separate outlet that takes us from heated to or cooling side of the system to DHW, and a diverting valve is built in there to give us a priority level there. So the domestic hot water will be prioritized over your heating and chilled water circuits. And we've also added a backup energy source. So there's electric backup in all of these indoor units, and it changes based on the size or capacity of the unit itself. So some specs that kind of match the outdoor unit we just looked at there earlier. You see that you've got the capability between 20,000 to 58,000 BTUs on the unit itself. Part of that is because we've got some electric backup in the indoor unit here. So if we have a period of time when the outdoor unit's just not there's a temperature outside that it just won't be able to function and give you the temperatures and BTUs that you're looking for, we can kick in the electric elements at that particular point in time based on the outdoor temperature. And now the electric heat is kicking in and taking over the operation of heating the space in your domestic hot water. And there's also a separate amperage here, a 40 amp and a 50 amp, depending on the size of the indoor unit that you're looking at here. Little higher amperage here because we get a little bit, an extra 3 kilowatts of electric elements in that larger unit to deal with there. So we got again, a 240 volt single phase indoor unit, and with a 40 amp breaker and a 50 amp on that one. And water flows, we looked at a little bit, but your max water flows here, 4.4 up to 12.75 on the indoor units with the ECM built-in pump on that. And there will be some temperature, just to kind of review some of the temperatures here. The maximum system temperature, which is relegated by the electric elements really as far as space heating goes, you're at about 75 degrees Celsius. There is a operating limit here auto reset limit here that we'll see at about 165 that will kind of cycle that automatically on and off. So that's our max temperature there. And you might need that max temperature if you're doing domestic hot water, for instance, on this indoor unit, and we're supplying that energy to an indirect tank. We can set the supply temperature for DHW. I think the maximum is about 131 degree Fahrenheit. The heat pump itself will be able to give you the outdoor unit maximum temperature is 140 Fahrenheit. So that's why the DHW temperature setting is about 131. So we have a little bit of a temperature differential there to ensure that we can meet that that set point target for the DHW tank. If it can't keep up, then of course the electric elements will kick in at that point, and then we'll start to heat the tank via the 6 kilowatt or 9 kilowatt elements, depending on the unit. Our supply temperature targets for space heating, maximum is 140 Fahrenheit. We saw that in the graphs already on the curves. Minimum is about 68 degrees. This is your supply water temperature going out. So if we're doing outdoor reset, for instance, we might start out at like 68 Fahrenheit in a radiant system, and then go up from there as the temperature outside gets cooler. And that's for both HC1 and the mixed circuit 2 for heating. If we're cooling, that set point for supply temperature is going to be from 45 Fahrenheit to 68 Fahrenheit. And that's the minimum temperature we can hold in the buffer tanks, about 45 degrees Fahrenheit. A manual reset of 186 or 86 degrees Celsius. When we add in, there's an option in these units you'll see in a bit where we can actually add in a backup boiler that maybe you need more than 9 kilowatts or 6 kilowatts of backup, and you put a larger electric boiler in there, or you have a gas-fired backup piece of equipment, and you're going to program that when you're doing your commissioning of these these heat pumps. And when you tell it that you're going to use a different source, it's not going to be the elements in the indoor unit. It actually disables those limits so they don't interfere with the operation of your system. Right, so we'll disable that. We'll allow it to go to a higher odd adjustable high limit for the unit itself. The tanks, we kind of described, we do have a buffer tank that comes with these units. This is what it looks like inside as far as the piping inside there. There's multiple tappings, multiple methods of heat exchange inside of this thing when you're dumping heat into it and pulling heat out of it. So it's very important that we pipe it the specific way that it shows in the manual. But we just get under 20 gallons of reserve here. So if we're doing cooling, for instance, we have about 20 gallons of reserve chilled water in there. If we're doing domestic hot water production, switches over and the unit goes into heating mode to heat the tank up, we still have that reserve to give us the the ability to keep the building just keep cooling it down while we're doing the domestic hot water production. The size of it, it's not it's just under 2 feet as far as the total height there. The diameter is about the same as our tanks. You're going to have a look at that in a minute. You can actually integrate this into a tank if you're paying attention to the first slide we looked at as far as the arrangements. And the range of temperatures, we can go from 45 degrees Fahrenheit to 230 Fahrenheit, 7 to 110 degrees Celsius on these. And the tappings, we don't use all of them. As a matter of fact, when we get into the control or the piping arrangements, the application drawings, you'll see that we don't always pipe the backup heating system, like a boiler or whatever, directly to this buffer tank. We might do it a little bit differently for a specific reason. We'll try to explain. But there's a couple of tappings. The A one here is just plugged off. We don't use it. Then we've got your supply B to C is essentially your heating or chilled water circuits. Your supply at the top dumping back into the tank at the bottom here, supply return. And then F and E. F or D and E here, are the outdoor unit supply and return. So we go D to E here, and we got a sensor port that we're going to use, an I. There's another sensor port here for H that we don't use. And then the backup auxiliary heat that we show here is F and G. We'll show you in the arrangements. We don't always use this tapping, especially if it's just domestic hot water production, and we'll give you some reasons why we would do that. But there's multiple tappings in here that you can use for your system. You have a couple of tanks that are going to be available. These are not quite available right now for the release. So when the heat pumps come out, they'll be a little bit delayed, but we got some backup there to kind of to get us by in the meantime. If you're looking for domestic hot water tanks, 52 to 66 gallon, they're glass lined. They do include an anode, electronic anode in there, a very high quality anode that Viessmann's been using with this company for years in Europe. And it's going to match the indoor unit as far as the color, that white Vitocal white color. And there's really no assembly on site. It shows up on site fully dressed here. The capacities of what we're looking at, your 52.8, 66 gallon, 250 liter tanks. Your range here, as far as your temperatures go, are all based on the outdoor unit there currently. If you have a backup boiler or your electric elements, that set point could be up to 60 C. There, typically that's where we kind of limit our domestic hot water set points, no higher than 60 C unless you do some sort of an override. But that's available. You can see the diameter is about the same as the indoor or the little buffer tank. And the idea is that with these tanks here, we can stack the buffer tank on top of these smaller tanks, your indirects here. And now that's for space savings. Or some areas you see a look at what you have in that mechanical room when you add a heat pump in. I know in Vancouver here, for instance, square footage is very valuable. So being able to take that tank, that 26.5 inches, and kind of move it on top, so you're gonna leave a lot of footprint there left over that for other things to kind of go into that space. So it's a really good space saving idea here. We can't flip it the other way around. The tank is with water in it, it's going to be way too heavy. It will crush the jacketing on the buffer tank, but it will easily fit and slide on top of your indirect tank like that. Little anode. Not going to spend a whole lot of time on this. There's a little bit of a letter from the manufacturer here. The next one, but these are pre-installed in the on the tanks themselves. We just have to wire them and wire and get power to them. Lots of fault information, polarity issues, stuff like that. It would kind of point out that you have some problems if it was installed incorrectly, that sort of thing. Very reliable, robust as far as the functionality. It's a titanium anode. We have the manufacturers in to our training facility in Waterloo there earlier in 2023, and they kind of went through their whole gamut of information on these things. So very reliable anode here, and to the point where they're saying lasts longer than a stainless steel tank without corrosion protection. So it's a pretty lofty claim there. We are a tank manufacturer here. All of the tanks that we're going to be talking about are come out of Falkmont, France. And as I mentioned, we've been using this particular anode for a number of years in conjunction with our ceramic coated tanks that we sell in Europe with some very good results. And this is a letter from the manufacturer here, just kind of pointing out that they've tested these as far as their ability to protect the tank from corrosion, down to some very low conductivity levels here. So this is kind of a 100 milli MHOS, which is just ohm spelled backwards here. So this is kind of a resistance thing. It's kind of the typical of a microsiemens or conductivity. So it's essentially something with a very high level of resistance, very low amount of conductivity that we're dealing with. They test to 100. Some of the worst water that we're looking at here is in this area in Sudbury, Ontario, talking about 383, and that's still 4 times better than what they tested to here. So as far as their reliability and their confidence that these things are going to protect your tanks, they're quite confident this is going to be every bit as equivalent to a stainless steel tank with this anode being installed in it. So nice quality on that side. The indirect tank that we will be bringing to market here will have lifting handles on it, and they're loaded to each set of handles. There's ones on the top, one on the bottom here, so you can, guys can grab it, lift with your legs, not with your back. And they are about 536 pounds per set of handles there. So a nice and heavy capability there. That just allows you to get this in. What I like about this as well is that you can see that we got a high level of insulation on these tanks, very typical of our tanks. So very low heat loss. And we are dealing with some fairly low temperatures to begin with. And the idea is that if we got that heat stored, we want to lose as little heat as possible. So I think it was like the numbers I was looking at were like, I think it was like 0.83 kilowatt hours for every 24 hours you're as far as the heat loss goes. So very low level of heat loss in these tanks, very reliable. And they're also sized based on the requirements of low temperature heat pumps. So the big surface area. We are also testing our stainless steel tanks in the interim. Should you need domestic hot water capabilities, we will have all of our tanks stainless steel line also tested for the temperatures to give you an idea what the performance is going to be with the surface area we have in those tanks. So we make those in 2 coil as well as single coil. So we'll have that coming out as well. This slide here is for the service tech, really. As far as the installer of the heat pump, uh, you will not have to have a ticket here to install the heat pump. It's all plumbing connections, but you may need to have a ticket to actually buy this from a wholesaler. So looking at the top here, in the US, you've got your 608 type 2 or 3 or universal is your refrigeration ticket. In Canada, you've got your residential 313 or commercially your 313A certification. And if you have to do service on this, you're opening it up and opening up on the refrigerant side here. All we're going to be doing when we're installing these things is essentially connecting and purging out the hydronic side of the system, the glycol water mixture. But as far as any service, it's have to know that these are A2L, mildly flammable refrigerant. Lots of videos online about showing like lighting this stuff up and how it does. It effectively almost snuffs itself out. Mark had mentioned, I think, in one of his presentations earlier on that, like, I mean, the lower explosive level of this stuff is like 38% in the air. And you're only dealing with this heat pump here, outdoor unit, for instance. If it was a smaller one, it's just under 2.5 pounds of refrigerant in it. So sitting outside, you know, very difficult to get that 38%, of the LEL there. So, as the wind blows there, the flame speed's only about 6.7, feet per second or whatever. It's very low as far as propagation. So it almost blows itself out with a little bit of a wind. Uh, but you want to make sure you have all the precautions here, right? So it's always being always being out safety and ensuring that we're doing the right thing. So make sure you have static electricity, you're grounded, you're turning all the power off, everything's ventilated correctly. You've got some sort of refrigerant leak detector or whatever that's appropriate for this refrigerant. You got a fire extinguisher, CO2 or powdered one, to make sure that that's the type of extinguisher that's going to actually snuff this flame out should you need it. And if we're storing it, the storage temperature from -13 Fahrenheit to 158 Fahrenheit, that you may need to have, I know warehouses, we're going to have them stored here in our local warehouse, and then they'll be looking at certain explosion prevention plans that might be required based on your authority having jurisdiction in your location. So just a little bit of a blurb on that. It is A2L, it is flammable. But like I say, if you have any concerns about that, you just kind of look online and you can see there's very little concern about the flammability as far as that goes. But we do have to be preventative here and make sure we follow all the local protocols. And all these tools here, for instance, this is one manufacturer. I know, talk to the guys at Testo. They're ready to roll. They got R32 tools as well that are all approved and ready to go. So everything you can think about, for servicing R32 equipment is available now out there for you guys to look at or to purchase. The exploded diagram I mentioned a little bit earlier that we would look at, and looking at some of the safeties and stuff as we go through, but we just highlighted a couple of things in here just to kind of explain a little bit about these outdoor units. The wind deflector I mentioned in the fans, we don't want this fan kind of pointing right at the headwind, so not right down the channel or right down the pipe as far as the wind. We would want you to offset that a bit, but there is a wind deflector as part of the screen. You can see it here. That will help to offset any issues as far as wind on that on the head of that fan. but in the manual it does mention about where you want to set that. It is fairly low as far as your noise level off of these outdoor units, like 60, 65 decibels, I think it is. But, if you put this fan in a location where, it's off the wall or in an alcove, you could start to resonate that and, amplify it. And now all of a sudden we've got a little bit higher decibel rating. So just, follow your guidelines as far as installation of these outdoor units. Inside of the unit, in the cabinet, we've got the picture of the compressor with the cranky heater. You'll see a better picture of that in a second. You've got your glycol to refrigerant heat exchanger here. So this is where all the magic happens, where we're either dumping heat outside in the cooling time, or we're pulling heat in from the outside and dumping it inside. It'll all be part of this little heat exchanger here. That's our refrigerant to glycol. We have another heat exchanger up top here. And it's for the enhanced vapor injection function. And with enhanced vapor injection, typically you're going to have two expansion valves. One is the regular refrigerant process electronic expansion valve, and then we have a second expansion valve that's going to be part of the EVI component there. And we'll have a look at that as we go through. So a little better picture, actually. Nice photos shot here of the inside of these units, so you can see the little heater on the base of the compressor here with the built-in accumulator. You've got the big refrigerant to glycol heat exchanger sitting here. This is where all of the heat's being exchanged, and there's your connections. Those would be 1-inch PEX adapters that we're going to supply that will be connecting here. And we use a reversing valve, electronic reversing valve here to go from the heating to cooling. And again, you do that switch on the unit itself. And a picture of that extra heat exchanger we added in here. This is going to be standard on all three units. It's not an option. It just comes with it. You don't have to order it. It'll show up on site with the EVI component already built into it. It's going to run, enhanced vapor injection is going to run in the heating mode only. You're going to have a look at what that's all about. And we use electronic expansion valves, not thermal expansion valves. These are usually a DC voltage connection here, kind of like a gas valve, really, as far as DC voltage. And it's just a coil, and we can modulate that a little needle valve inside of this enclosure in the body by pulsing a voltage to the connections here. So that kind of increases or decreases the flow through the valve inside. And the limits that we have built into the outdoor unit, just already mentioned the flow switch that's available. It's going to be part of every single, it's going to be on the hydronic side there. So we don't have our appropriate flow, that compressor is not going to start. And we also have low pressure and high pressure switches there. And of course, if these start to operate, then that's usually some concern, and look at what's causing that, some service possibly. But the low pressure switch is going to cut out at 7 psi and cut back in at 22. And the high pressure is going to cut out at 638 pounds. And it's going to cut, that high pressure switch is going to cut back in at 464 pounds. So those are all safeties that are built in to the outdoor unit that we're looking at. Just a little picture of the enhanced vapor injection. If you've never seen it, it's a part of the whole with the R32 refrigerant. We kind of get a little bit of a boost as far as our capabilities in colder areas of the world with this technology. And the idea is that this extra little heat exchanger out here is actually doing some of the work that would otherwise had to be done by the compressor itself. So when we add the work done by this portion into the compressor, we actually boost out the temperature that we can get to on the compressor itself. So if we look at the flow coming out of the compressor, we're in heating mode. So the reversing valve is in the heating mode. High pressure vapor going through, goes through a condenser. Right, we're going to condense that vapor into a liquid. It's going to give up its heat as it does that to our heating system. So our pump is on here. We're pumping that return water in and pulling the heat off of that heat exchanger and bringing it out to our heating system. That high pressure liquid now is moving out of the heat exchanger here, and it moves into this EVI heat exchanger. Some of it, if we're going into EVI here, the solenoid valve will be open, and now refrigerant will be able to bypass high pressure liquid is going to be able to bypass here, go through our electronic expansion valve, which is going to pull some heat off. It's going to cool, drop in pressure. Now we have low pressure liquid. And what that's going to do is actually going to go through the other side of the heat exchanger, and it's going to pull heat off of this high pressure liquid going back out to our outdoor unit. So it's going to heat this line up while cooling this line down. And now that low pressure vapor is now injected into the heat pump or into the compressor of the heat pump specific area. And that's going to boost the functionality or the temperature we can actually get out on the high pressure side here. So we're doing some of that work right here and dumping it into the compressor. The other benefit is as we pulled heat off of this line, which is going through the electronic expansion valve on the refrigeration process, now low pressure liquid, this temperature is lower now going into our evaporator. So it's going to be able to have a better delta T versus the outdoor air temperature. So we're boosting the capacity of the evaporator here as well, which in turn goes back through and helps to boost the capacity of the heat pump itself. So we have a kind of a, two bangs for your buck there with this enhanced vapor injection that allows the capacity of the heat pump to actually increase. So that's a little picture of what enhanced vapor injection looks like and why we use it. The connections on the indoor unit. So you've got the electrical connections, your 240 volt single phase at the top there. We've got a bunch of 120 volt and sensor connections that we're going to look at here, as well as our indoor-outdoor unit communication connection, which will be a twisted pair between the indoor and outdoor units, a Modbus communication. So we want to have a twisted pair there, not a solid core like thermostat wire to those. Expansion tanks built into this unit. So it already has expansion tank on the right side of the unit pumping away from the circulator here, and that's connected at the back. If you leave about 12 inches of clearance at the top, that should be enough for you to actually, if you ever have to remove this and service it, that it's going to be easily to remove. There's two auto air vents, one on the supply, one on the return to help get the air out of that system. The circulation pump sitting on the right or left-hand side there, it is responsible for pumping through the outdoor unit, through the indoor unit, and also to your buffer tank or to your indirect tank. So it's that one circulator does all of that process. The supply side of the system, we've got electric elements sit on top here. There's your thermistor to pick up temperature. Is that temperature high enough? Do I got to kick in the electric elements? That kind of sits right in here. There is a bit of a time delay in that electronic backup that we can say we delay that off for a certain amount of time before we kick it in, just to make sure the heat pump has essentially reached its capacity. The three-way valve is connected to an actuator, which is a 120 or 240 volt actuator, and that is you can manually operate that as well. You just pull this little dial out, and now you can manually turn that back and forth for kind of manual operation for testing. And the indoor unit has its own pressure relief valve inside of it. To have a good look at how the fluid flows through this unit from the inside unit to the outdoor unit and to your system itself, we look at this side here. So if we start off with the system return and we come in, you see there's the expansion tank teed off that's sitting at the back of your unit. It comes in through here. There's a little pressure sensor picking up our pressure in our piping system. Goes to the ECM pump, which is pumping away from our expansion tank. Goes over to our little manual air vent here. That's a nice spot there to pop the air out. And then it goes through our return sensor. And then that's going to go to the outdoor unit. It's going to heat up in the outdoor unit, come back through and supply into our supply side of the indoor unit. There's our PRV sitting there. It goes through our electric heat. So this is where it's going to, depending on how you programmed it, will those elements kick in or will there be a delay before it kicks in here? We get out with the appropriate temperature. This is kind of a feedback that says we need more heat from the heat pump or whatever, that feedback here for not quite hitting the right set point. And then we're going to go at the fork in the road here. So we're either going to have system supply, whether that's heating or cooling, or we're going to have domestic hot water function. So it depends on whatever's calling at the time, where the position this diverting valve is going to be. And then for that system or DHW, it goes back around and then it comes back in and the whole process starts over again. So nice real layout. It doesn't actually look like this inside of the unit, but this kind of really organizes it so you get a really good conceptual idea of how the fluid flows through that system. And now all of the inputs. So we got a number of inputs on these boards, and that's why there's a real value in these indoor units as far as their capability. They're effectively another control on the wall here, but you have a DHW recirc pump, which allows you to do time programs and functionality on the recirculation side of it. All of the pumps are about a 2 amp max fuse on these systems, which are for a residential unit. That's very appropriate as far as sizing of the pumps, as far as your amp capacity. There is a glycol circuit pump here, and we won't show you an application in the drawings we have here forthcoming, but you will see that there is the ability, if you want to separate. If you wanted to just run water in your building, you could add a heat exchanger, and there's another essentially a glycol pump output that we could use there that would now allow us to have the glycol loop on one side, and then the indoor unit and stuff will be piped with just water throughout the whole system. The issue with this obviously is your supply temperature. You got to remember that you're not, your supply temperatures being what they are from the outdoor unit, you are going to sacrifice some of that supply temperature when you add a heat exchanger. So you got to critical to design that heat exchanger for its proper functionality in this system when you do that. We have heating circuit pump output 120 volt. We got a heating circuit pump 2 output 120 volt. So if you have two temperatures, you got your heating and cooling circuits, I should say. The boys didn't correct me there. They must be asleep right now. But heating circuit 1 or cooling circuit 1 pump for chill water, and the same with HC2. HCC2 is what it should be here. We have a mixing valve, 120 volt floating. We're going to look at that here in a moment, what that looks like. It's a standard Viessmann mixing valve. If you've ever installed, a Vitocal with mixing valves, or, a commercial boiler with mixing valves, it's a standard 120 volt floating Viessmann mixing valve we use there. And then all of our sensor inputs. So you got, your heating, cooling sensor inputs here. Domestic hot water tank. There's a room temperature sensor for HC1 that you can go room temperature feedback, and then of course an outdoor sensor connection. And over here on N, you got a backup. So this is where we would program if we didn't use the electric elements inside the indoor unit. We want to have a boiler backup. We program it, and there's our dry contact to enable that appliance when the time comes in the season to have that auxiliary heat. And if you want to operate your cooling and heating with like a TT contact instead of just constantly on, you can remove the jumpers here, and now you can add your cooling demand or your heating demand in this spot here, and that will enable and disable the associated pumps out to the system. And this is the schematics we're going to look at. So we'll kind of run through these, give you an idea. This is a system without domestic hot water. So we have a fan coil here that's going for heating and cooling. So that's a chilled water coil in there. And you can see the outdoor unit coming in and from the into the indoor unit. And then the diverting valve would be positioned for space heating here. And we've got a sensor in this little tank, little sensor sitting right in here. And that's going to load that tank up to whatever that sensor requires based on the outdoor air temperature. So we have to do an outdoor reset here. And you see the tappings here. So there's our tapping for our heating supply from the indoor unit, return back right here. And then the buffer tank is, supplying the heating circuit here, whether it's chilled water or in the heating application. And we have a thermostat here, and that could go back again to that contact on the right-hand side, and we could be doing enabling, disabling space heating and cooling with that connection versus having it as a constantly on based on an outdoor temperature requirement. The other option here is we add in a backup boiler, and we add the backup boiler in here. We recommend putting a diverting valve in. The diverting valve does not block off the return here. It's still connected to the expansion tank, the outdoor unit here, but it does block flow from the indoor to the outdoor unit. We also have a relief valve, pressure relief valve in the outdoor unit as well to protect it from any pressures. There's a relief valve in here as well, but you see the backup. We're going to disable the electric heat inside of the unit. And we didn't use the tappings here. We probably could have in this application, could have added these connections here. The idea is if we add the backup fuel source to as a closest space T system here, when it supplies into our unit, and it goes out here as far as a supply goes, then if I had added domestic hot water to this system later on down the road, it would be able to, this boiler would be able to heat the tank at DHW as well. If I pipe it directly to the buffer tank, unless I do a bunch of sophisticated piping and relays, it would be difficult for this boiler to actually heat that domestic hot water tank. But it's essentially sitting there as primary, secondary. If I added a DHW load here, it would be able to heat that system up without a problem. Diverting valve is in here. The reason why we would do this is that if we're using the boiler here, we could use the pump enable output here to essentially enable this diverting valve so that we don't have flow to the outside when the boiler is actually the main source of heat here. So we essentially isolate the outdoor unit from operation. It's going to be a cutoff point we program in to say heat pump is not going to be on during this time anyway. And so it's going to be sitting idle outside. The heater, the crankcase heater and all that stuff will still be in operation. So we don't have to worry about that side of it. It's glycol in the unit as well. So we don't have to worry about any freeze ups and stuff in the outdoor unit when we're doing this particular type of function. And there's where we add the DHW. So now we've got this system here, no backup. We're using the electric elements here. And you can see that we got the two supply tappings. One goes to the tank, which just feeds back to the system here on the return side. Right here, sorry. And of course, the supply to the buffer tank hasn't changed here, back on the return, back to the system, and our heating and cooling circuits pulling off the buffer tank. And if the domestic hot water calls, the diverting valve will operate here, and we block off the heating or cooling function to the buffer tank. But there is residual capacity here during domestic hot water that we can maintain heating or cooling of the building with that mass of energy still loaded up in that little tank. And now we've got electric boiler instead of a gas-fired boiler here. We've disabled the electric elements. The diverting valve is in position here, operating the same way as it was in the previous drawing. But now you see that when the domestic calls here, if I was piped to this electric boiler to our buffer tank, there'd be no way for that electric boiler to kick in to actually heat this tank up. If I connect it with closely spaced T here as a primary secondary type of a function, now independent of whatever's calling here, the heat is going to go to the indoor unit here first, and now from there it can be dissipated wherever it needs to go as far as the load goes. So just kind of some conceptual drawings that we've come up with. First look at HC2. So we have a radiant heating system here. During the heating season, the mixing valve here is looking at a temperature sensor. There'll be a sensor connected to the unit, and now it's adjusting the supply temperature out based on outdoor reset. So we have a heating curve for this fella. We have a heating curve for the fan coil here. And now you're going to do sensible and latent cooling. You have both of those loads capability in the summertime when you're doing cooling. You can actually turn both of them on. In cooling, the mixing valve here stays in the fully open position, and we have that chilled water going through at the same temperature as the outdoor or as the air handler. We would add in some humidistats or humidity control when we do radiant cooling, just to make sure that if this supply temperature is down below the dew point, we don't start having condensation start to build up in the surfaces of the floors, etc., that we're doing that cooling function on. So there's what that looks like. Adding in the electric back or space heating boiler backup here again, so a gas boiler backup. If nothing really changes here, other than, like I say, the piping, and we might add that little diverting valve in there for that functionality of automatically switching from, the boiler as the heating source to the heat pump being the heating source. Make sure that the fluid flows in the right direction when all that stuff occurs. And last one here is just a picture of, possibility. I look at this one here almost like a retrofit where you might have an air handler in there. But maybe it's an area where you need to design for more heating based on that lower temperature. So we add in some panel radiators into the space as well. And the idea here is that you could have these operate at the same temperature. This has got a built-in pump in the air handler here in this case, so we don't have to worry about the HC1 pump. That could be this guy down here in our system. And we also have the radiant cooling side here as well.
or heating side with the mixing valve with the supply temperature sensor moving out in the radiant here. The reality is, Patrick kind of mentioned there yesterday, really, you just need the temperature sensor connected to the indoor unit to open up your HC2. So you could also just have that sensor connected to a radiant panel like this. There's your HC2 feeding back, and there's your HC1 to the system. So you don't even have the mixing valve here. It's just feeding back that second circuit with the panel radiator. So it does open up a lot of flexibility here. A lot of times, like I say, it's always about talking to your sales reps, that sort of thing, and getting the concepts down and what you want to do. And oftentimes when it's planned out, there's a few things we can kind of look at and possibly make some suggestions to make that system that much more functional and that much more capable of doing what you expect it to do. That diverting valve is essentially just kind of a picture here, just showing you this is a generic uh, diverting valve. So not all of them look like this. It might be different, but the idea behind the diverting valve is in normal operation, the outdoor unit's feeding the indoor unit. So A to C is open, blocked is B to C. As soon as that backup boiler kicks in, the diverting valve moves to the position where it blocks A. So there's no flow between A and C anymore. The flow now is between B and C here. And as long as you don't have a check valve or whatever connected in this area here, then that the expansion tank is still directly connected to the outdoor unit that's in the indoor unit as well. So not having to worry about isolating that thing as far as having worries about pressures, etc. But that's just how the diverting valve is going to work in our recommendation there. Just a little blurb on this. Down the bottom right-hand corner here, it's just talking about an energy study back in 2018, and just talking about, the energy savings in an area. Minnesota is the area we're talking about here. So, it's kind of, very much like a lot of areas of Alberta and Saskatchewan here, Manitoba here, in some areas in Ontario as far as the design temperature stuff that we'd be typically dealing with, and just how even with those areas that they saw some significant energy savings when they went from just a propane or electric furnace and added in the heat pump here to offset some of those either the electric kilowatts electric furnace or the BTUs from the propane furnace here. So there is some savings there. There also is savings in as far as incentives go. I know here locally in the Lower Mainland and BC, the utilities are offering incentives to replace your gas-fired appliance, whatever, with electric or a heat pump, as well as municipalities are kind of kicking in. The province, I know down in the U.S., some of the states are dealing with it. Some other areas. Our friends from HeatSpring actually sent out an email. So if the guys at HeatSpring there, they do a lot of the education training and stuff like that. For a bunch of different technologies that we're all involved with. And they had just mentioned that New York State has an incentive program there that they just launched out there. So it's just if you just do a little bit of research in your area, I think you'll find that you'll probably see that there's probably a number of incentives for you to remove that fossil fuel appliance and add in a heat pump there. So some ways of offsetting those costs to your homeowner. Again, all this stuff would be, you just don't go and buy this stuff. It'd all be through when you're doing, applying for incentives and rebates. They want to make sure that, it was installed and done by the appropriate authorities and, people have the right trade qualifications. And again, in the US and then in Canada, those qualifications that we've been looking for on these units are sitting right there. The outdoor unit will come dressed as far as a package goes. It's not dressed. It actually comes in a box, these parts. So some air elimination devices, a separate relief valve you see here for the outdoor unit. So that's going to be coming in a box. As well, we got a hanger for the outdoor unit here. All the sensors are supplied that I mentioned, and some of them are optional. Some of them depend on what you're going to do. So the HC1 supply sensor is typically your buffer tank sensor that we would install. We have an outdoor temperature sensor for outdoor reset. So you can do fixed temperature or reset temperature with this unit. Room temperature sensor for feedback. And like I say, the more finite your supply temperature for ideal comfort or whatever is all going to be essentially decided upon with a lot of different inputs. So the more accurate the inputs are, the more precise that supply temperature is going to be, the better this outdoor unit is going to function. So that room temperature sensor could be very valuable in some of your applications for those circuits. And then there's a fuse and resistor. The resistor is an inline resistor for communication to the outdoor unit from the indoor unit. And there's a fuse that's a spare fuse for the indoor unit itself in case there's something that happens there. We'll also be supplying all the stuff you see here with the connections going to the 1-inch PEX A adapters that will show up on site as well. So you bring in your 1-inch, PEX, and we've got the connections between the outdoor unit and the indoor unit already, in the box ready to go for you. There's the mixing valve that we are supplying. It's a 120-volt floating mixing valve. We've used these. I've been with Viessmann for almost 16 years, and this is the same actuator we've used since I've been there. The sensors have changed. They're all 10K NTC sensors that we use now, and all the sensors we looked at here are all 10K as well. So very common resistance sensor out there in the market. And just a final picture of what you look at, what comes as a package on the left-hand side. That's all going to show up as one, one piece of equipment. This is not the part number, but these are just the different sizes again to kind of just reiterate what we're looking at here. The optional indirect tanks that will be available. We will have the stainless steel tanks essentially engineered with all the performance information that they'll be in the interim a good fit for you. And then we have the optional mixing valves. Should you add another mixing circuit onto that system that we can add in there for multiple temperatures. Temperature design. So again, when we're looking at these systems, it's looking at the charts. We're going to get a BTU per hour based on what the ambient temperature is and what the supply temperature possibilities are. So keep that in mind when you're designing these systems to make sure we get the right match for heating and or cooling in that case. And just a nice picture there to finish us off. I hope you enjoyed this little bit of a presentation. We walk through a little bit of the key features of the heat pump itself, what we're going to get, why we name it, what it is, what you're going to get on the skid. The benefits of the indoor unit, like I say, it's like having that heating or building control built into the unit itself. So there's a lot of advantages of having that kind of show up on site and not having to figure all that stuff out on your own. And then we've also identified again some of those advantages and looking at some of those application drawings where we would want to kind of think about things like adding in heating circuits and where to pipe the backup heating and all that kind of stuff. So there we go. So that's it for the presentation. Let me turn my camera back on. How are we doing, gentlemen?
Doing well. Excellent job again.
All right, thank you.
That Pro Toolbox there, if anybody wants to scan it, or that current product manuals, you can find the TDM install manuals, all those good bits of information on this product.
Yep.
Ready for ordering. All wholesales absolutely have been provided pricing, so you can call them and get all that information. And pretty soon for a turnaround. We're almost so turnaround. I should be 6 weeks or so, maybe 8 weeks at most. Be in your hands for install. So we're hopefully mid-April to beginning of May will be delivery to wholesale. So excellent job, Scott.
Yeah, thank you. Now's the time to kind of speak with your wholesalers and stuff and get those timelines arranged. So if you got those projects, we're hitting into spring here. You get some of those projects that are kind of sitting there waiting, and you're kind of looking at this. You can certainly give a call and get all those things firmed up and identified when everything will essentially be available to land on site for you guys.
We do have a couple of questions. It was actually first one that came in was real early. I meant to just type an answer, and I hit answer live. So I've been holding it here just so I didn't forget about it. It was about, does Viessmann specifically sell a raised pad or a sling mount for the outdoor unit? Currently, right now, we do not. I know product management is looking into a bunch of alternatives for that. All the weights are listed in that TDM, and I'm going to go ahead and presume most every wholesaler on the market probably has a generic brand they might have that'll that'll work for those snow loads and anything to get that above.
Or pads.
But we are absolutely looking into it. There was a nice recycled one we saw. So I know the product. It's on the mind of the product team. So hopefully we'll see that.
Absolutely.
See one in our portfolio soon.
A good point.
We kind of always talk about this, and it's a great question. Can we use a non-Viessmann boiler as the backup for this system?
Why would you want to?
That's exactly. It's it'd be nice, it'd match.
But yes, you can.
Yes.
Absolutely.
Just close contact to bring on. I mean, if it's an existing cast iron oil, if you want to leave that guy in there and have that backup, absolutely. You're just close that L8148 and that thing will take off. So
absolutely, that's as long as it's got a dry contact capability. And the other thing is in the drawings that looked up, but I think is a clever thing to add the diverting valve. You just want to make sure you have parallel and output or whatever to that, so that diverting valve does its job as well in that system. Should you have the diverting valve added into your piping arrangement?
Yeah, and I was looking at the cost of it, buying the 120 volt diverting valve versus all the relays to go to a 24 volt diverting valve. Your bits just buy the 120. Your bits just easier.
Keep the mechanical switches to a minimum, right? Just more stuff to break. So I agree
100%. The drawings that Mark was so gracious to do with us show external air eliminators and expansion tanks, and is that a requirement or recommended, since we do have some air elimination and an expansion tank built into the indoor unit?
I think you look at that as for me, air elimination devices, I put them wherever I possibly, you get there. Air is the enemy. And like I say, most of the problem systems out there are the ones you walk into. There's not an isolation valve. There's not an air vent in the system. And you replace a pump or do some service. Now it's like you're 3 hours trying to get the air back out of that system. So to me, putting air vents in different locations absolutely is especially with glycols and things like that you're dealing with. And the low temperatures we're dealing with here. So good scrubbers are always a good idea to have, like we're going to with the Cleffa unit, for instance, that we have in the outdoor unit. And the expansion tank to me is, it just depends. You know what I mean? As far as your expansion goes there is the one inside the unit. And we're told that is a extremely robust little expansion tank in there. It's piped in the right spot for it to kind of last a long time. But there might be the having that redundancy where you got possibly more serviceable, one sitting on the outside you might want to have there as well. But
can I jump in here just because you guys let me in? I
feel like I was actually going to say something. I thought you muted this guy. I saw he unmuted himself. I was going to let him go. So
we even get camera. There he is. Thought that I throw my 2 cents in there, right? In the drawings that we showed, the very simple drawings with the air handler and the buffer tank, you probably don't need another buffer tank or expansion tank. But if you're going to put a bunch of radiant floor, that extra piping, that extra surface area, that's when you might need to add the extra expansion tank. And the thing about expansion tanks is it doesn't hurt to put more in. The only downside is the cost of putting it in and the cost of the tank. So you might want to look at it, say, well, is it big enough? Is it not big enough? We give you the size of the tank in the TDM, and you can decide, is that enough for the building I'm putting it into? And if not, I add this other one that we show in the drawing. It's not a requirement. It's really a system choice based on how you're piping it.
Okay.
And also, if you do add the backup system, any backup boiler of whatever brand it might be, hopefully it says Viessmann on it, of course. If you do add that diverting valve, you are still open to the expansion side of things because it's on the return, but you are going to cut off that discal Cleffa air separator that's attached to the outdoor unit. So adding that other air elimination, and there is that auto vent on top of that resistance heat inside the unit, but a tiny little can vent inside the it's great to have it there for kind of a redundant backup. But absolutely, we should be adding something to that system as well that's going to work for everything. And to your point, Scott, you break into a system with glycol, even harder to get the air out of the system than it
Yep.
is with just pure water. And recommendation for insulating the PEX. Absolutely great question. I don't think we've actually talked about insulating any of the pipes in any of, I can't remember talking about it. Maybe Mark did when he did one. So
I don't think we talked too much about it, but especially if we're dealing with chilled water,
yeah,
it's important to insulate the pipes because you're going to have sweating inside a house. But the piping from outside to inside, I don't think we have any specific recommendation for it. I think you treat it like anything else where you're dealing with an unconditioned space. I know that, looking at our solar systems as an example, guys who are trying to use like Armaflex, and that works as an insulator, but the problem is the birds like to eat it too. So something that protected from the environment, critters and things like that. But as far as a thermal insulation, treat it just like any other conditioned pipe outside.
Yeah, good question.
Yeah, I know people that kind of build their own insulation, kind of put it in some conduit and Armaflex with some PVC over it to kind of protect a little bit more, but definitely PEX through the wall so we don't get that vibration through the envelope of the house and stuff. And then in a retrofit situation, could you install this air to water heat pump to an existing boiler to help with heat load only for fuel cost reduction? Oh, yeah. I mean,
absolutely, man. That's brilliant. But yeah, like you could think about like base load type of operation, whatever, right? Where you look at that, where that heat pump is going to cut off as far as your energy, whether it's temperature or BTU requirements, and then your boiler kicks back in to pick up the deficit. There is absolutely.
Yeah, there's some
I
nice
see that being a big part of it.
Yeah, controllability of that backup heat source as well. So you can run it two different ways. Either you tell the indoor unit to run it in kind of an automatic or what we call bivalent mode. So that's like heat pump comes on always first. If it can't get up to temperature within a time frame that's adjustable, it'll then kick in that backup source. Or if you want to size it in a retrofit that might be even a high temp application, and let's say we can run 110 to 140 for 75% of the season, that heating season alone, then you could say, okay, this is sized to go down to maybe a 20F or that negative 10C. And anything below that, I want you to run the backup source. So now we're just only running combustion in a very small window of that heating season. And the heat pump takes care of all of the shoulder and maybe a little bit outside of shoulder. So many different ways to look at that, even to use that to circumvent those high temp applications and the fuel costs associated with that. Because, we can still induce convection on baseboard down to the 120s, 130s, cast iron baseboard even lower a little bit by 110, 120. So cast iron radiators will still have convection at low temp. But again, how many BTUs are they putting out? Is that good enough for the space? Have they increased insulation, building envelope, new windows? A lot of different things, a lot more math involved with heat pumps. No more 85,000 BTU boiler puts out 82,000 BTU boilers.
That's right. Yeah. You just can't turn it up. Like a boiler, it's like, well, it didn't work at 120. It was just tried at 140. It's like this is a little bit different as far as a heat source goes.
How well do you think it would work in New England in cooling mode on radiant tubing in concrete with tile over? Yeah, radiant cooling it's great to do, but you got to remember that you can only do latent cooling.
Sensible.
So I'm sorry, sensible cooling and all the latent cooling, all of the humidity that we need to extract, all of that still has to go through an air coil. So in New England, I guess depending on where you are, me being in upstate New York, we do get a very long snap of high humidity. Radiant cooling is not going to be an ideal application for where I live. Coastal cities, you can do it, but you got to have humidistats. It's going to stop the flow of chilled water through the radiant cooling that your air handlers pick up what the radiant cooling wasn't doing anymore. there's a lot of control, third-party controls that come along with it, so it can work. Having it encapsulated in concrete will help with the sweating, but you could still drive that condensation out of the concrete through the tile and end up with slippery floors. Then if it's in, then you got to worry about all other sorts of things that you made a slippery floor, and so you can do it, but New England maybe not the best area to be like, let's do this new radiant cooling thing. It's great in the like high desert, desert areas and stuff. That works wonderful because there's so much more that we can do with it, but it will work.
Yeah, in tandem with the air handler, I think I could say it'd probably be a nice setup for sure. But be careful of your humidity.
We do have a couple of questions. I think we can actually answer these pretty quick. Let's see, expected lifespan, warranty of buffer, DHW and expansion, replacement of DHW buffer on top adds labors is covered by warranty. I mean, no Viessmann warranty has ever had labor involved with it. Not to say you couldn't ask for it, but most warranty doesn't cover labor. If it's if it's leaking from a manufacturer defect, of course, no problem replacing it. We do have warranty stuff, 5 years compressor, 5 years tank.
The warranty stuff is on the document side of the website too.
Yeah, that's already all posted for all that stuff. How long is the wait for the DHW tanks? We are told we should be expecting those around June. They just updated the testing procedures for North America for tanks, so we had to actually recertify them to a higher, it's like 2.5 times working pressure now, similar to a boiler, versus before it used to just be up to like 220 or 215 or something PSI. But they'll have a max allowable working pressure of 150, but we had to go back and retest them, so we should be seeing those hopefully around June is what we're expecting. Who makes the scroll compressor? Where are these machines assembled? They are assembled overseas, just like the rest of our equipment. And I believe it's a Copeland Quiet Series.
Yeah,
the Quiet Series, so it has a top discharge, so that'll keep the decibel levels down on it.
Okay.
Site-specific design review and assistance. Yeah, if you have contacts, you can always go to the contact section on our website to get in touch with your sales rep. Mark, Scott, myself, anybody in the academy. But yeah, if you got questions and pictures and this is what you're thinking about doing, we'd be happy. We got engineering teams, product teams that'll help with it. I think on the residential side, there'll probably be something more the academy and our sales reps will handle. But yeah, we'd be happy to assist you, anybody with that. Regarding rebates here in the US, 2 available, heat pump water heaters and heat pump for comfort. Does this qualify for both or just one? It's not a heat pump water heater. It is technically considered to be an electric boiler currently. I know, Scott, you mentioned this. They're actually catching up to the manufacturers for all those things right now. Depending on where you live, I know like Mass Saves has huge rebates right now. They kind of took it away from the combustion boilers and indirects, put it into heat pumps. So a lot of local rebates we're looking at right now. The only thing we're not seeing currently is like those Energy Star and the federal rebate monies available, but all of the manufacturers are working with the government to get that, forthwith and get those available to everybody. I'm sure the same for
what the hang up for
Canada
that is not that these equipment won't meet a standard, is that there's no standard to test to.
Right.
They haven't developed the standard yet. So this is where our engineering team and product development team, working with other companies around North America, to come up with an Energy Star or an efficiency rating for air to water heat pumps, because like Patrick said, it's really considered an electric boiler at this point. So it's not that the efficiencies aren't there. It's and the problem is there's no testing standard to test this efficiency. The manufacturers are way ahead of the regulators.
Yeah. Does the compressor shut down when the electric elements kick on? Yes. There is a
delay or something you can
yeah,
program
there
in
is a
there.
delay. They will kind of overlap a little bit, but it's just kind of during the handshake and the handoff period. If the outdoor unit can't keep up, again, that's why that time frame is adjustable. So if you want to hold the electric off for a little bit longer, if you are in those severe cold climate areas where it might take a little bit more for that heat pump to get up to that maybe 140 supply, then we can adjust that time frame out a little bit more to make sure those elements wait off a little bit longer. But it's a handshake, a handoff. And recommended surge protection for indoor and outdoor circuits. Surge protecting is actually all fuse protected. It's more the brownouts that we worry about as electronics manufacturers and such like that. So more of a line conditioner, especially if you're getting into an area that's prone to power outages. If you're always going to go into a generator, something that's going to clean up those sine waves before that dirty power from that startup of the generator gets to the unit. I know Mark unmuted himself, and I will let the more electronics expert than myself touch on that more than I can.
Now you put me in a big box.
Exactly.
Power conditioning, like Patrick says, surge protection is about lightning strikes, things like that. Power conditioning is about cleaning up the sine wave, and if it can't clean up the sine wave, blocking and opening and closing the circuit so that this electronic equipment isn't damaged. Anytime you have anything with a computer in it or any solid state electronics, you may or may not need power conditioning based on the current power conditions where you are. I give you a real world example in my own home this week. I had a weird power fluctuation happen, and I lost about 4 LED light bulbs that just dimmable bulbs that just won't work anymore because the sine waves just wasted the thing. It wasn't a lightning strike. It was just somebody's, on a transformer somewhere, and it took a while to clear it up, and it gave me problems. So in areas where you have issues with power quality, I would always recommend power conditioning on anything you have an electronic device for, your computers, your TVs, your whatever electronic systems you have. And that's really just the black and white of it. Again, power conditioning is different than spike protection. Spike protection is about surge, it's about lightning strikes, it's about things like that. But power conditioning is about protecting the electronics. When you have anything with a computer in it, you go from 120 or 240 volts, converts it to DC, and through that conversion, if the sine wave on the AC side isn't clean, the DC sine isn't clean, and then that's where the computer gets confused. That's my rant.
I liked it. That's perfect.
Yeah. Work for me.
And then does the Viessmann fan coil, our current or the older Airflow Plus or the new air handler, I would assume we're talking about, does that have a chilled coil to catch the condensate if we were to use those in an air conditioning mode?
The short answer is no.
No.
Viessmann is working on a chilled water, hot water air handler. The challenge we have is both the Airflow Plus and the new air version were not designed for chilled water, so they have a flat horizontal coil. There's nowhere to catch the condensate. You can use any third-party air handler that is chilled water, hot water compatible. Really what it is about where does the condensate go when you're in chilled water mode. We will have one that's coming in development right now, but we don't currently have one.
That cleans us up. Hour and 40 minutes, I think, with questions. Excellent job. If anybody has any more questions, I'm not in a hurry to go anywhere. We do understand that you probably have a day to get to, so we do really greatly appreciate your morning today with us, no matter what time it is or wherever you're located. Really appreciate your time.